Hello, my name is Johan Kraft. Today I'm going to talk about using visual trace diagnostics on Zephyr applications. My focus is visual trace diagnostics for simplifying embedded software development. I'm the CEO and founder, also CTO at Percepio in Sweden, and I'm the original developer of our tool Percepio Tracealizer. I have about 20 years of experience in artist tracing, 2 granted patents, and a PhD in computer science, which was basically about practical methods for embedded software timing analysis, a work that was done in close collaboration with regional industry. And before my PhD project, I spent my early career at ABB Robotics doing software development for their robot control system. You may have noticed that in Zephyr 2.6 there are some new options under tracing support. You can now select Percepio Tracealizer. By doing this, you include our trace recorder library, which is now adapted for Zephyr and is provided under Apache 2.0. The code is found under Modules, Debug, Tracealizer. This provides data for visual trace diagnostics using Percepio Tracealizer, and this is mainly targeting application development. Here is a screenshot of the Percepio Tracealizer. This supports several different RTOSes and also Linux tracing using LTN. You can run it on Windows or Linux. This provides live trace streaming over different data channels. You can use ST-Link, for instance, for STM32 devices, or a Sega J-Link, or you can use functional I/O, for instance, a TCP/IP socket or USB CDC, and this streaming framework is completely customizable, so you can actually make your own streaming solution quite easily. Just a header file under the Streamports folder. This is a commercial tool that we have developed since 2009, but it's actually free for academic use. So what do we mean by visual trace diagnostics, and how is that different from software tracing in general? Well, software tracing is the foundation. That's the input. A trace is a list of software events with, well, it can mean anything really, but they contain a timestamp, typically a quite detailed timestamp, microseconds or better. An event code could be like 42, meaning context switch or something, and some event-specific arguments. For instance, for a context switch, there might be an argument saying that the new thread that is resuming is my thread or something. The result can be something like this. If you output it in text format, you get a list of events, and that can be really useful for verifying specific things when you know pretty well what you're looking for. What happens at point X in my code could be, say, this context switch, what's going on there. But using a text log like this for debugging purposes can be quite challenging, because it's a lot of data, many thousands of events per second, and you might actually not know what you're looking for. Sometimes you only have some high-level symptoms of an issue, that your system has some kind of glitch or error, and it's not obvious to you how this would appear in the trace, so it's not easy to just search for it. To make this possible, we have a step we call semantic event processing, where we have a model describing the events that are traced and their semantics, their meaning. And the result is can be described as an object graph, a linked structure containing typed objects, for instance a mutex, and the tool understands what a mutex is, and that it has a state like an owner, and this is modified by known operations like a lock and an unlock operation. And the result, this linked object graph, can be visualized from many different perspectives and at different abstraction levels. And this makes it quite easy, or at least feasible, to provide really advanced functionality based on trace data. Based on this object graph, this linked model, it's possible to provide lots of different connected views that allow a top-down workflow that's really suitable for debugging, because you can spot anomalies in high-level overviews and then drill down into more detailed views to analyze the cause. In this illustration, for instance, we have a plot over response times shown in Tracealizer, and if we click on this outlier here, where we have an 80 millisecond response time, we can focus in the detailed trace view and see what happened at that point. So use cases are, of course, debugging, especially for multi-threaded RTOS applications, when you have issues related to multi-threading, resource usage like CPU load, memory usage, or software timing. And there are quite a lot of different issues that may occur that are related to at least one of these categories. Another case is when the target system can't be halted for debugging. There might be, for instance, a communication protocol with some real-time requirements. There might be like a heartbeat event or something like that. So if you stop the target system, the communication times out and everything stops working. In general, it's often quite nice to get a timeline of the software execution, so you really see that it behaves the way it's supposed to. Another use case is to analyze the application design. And I mean that in a broad sense. One aspect is to analyze the functional behavior of your application over time, like data plots, state diagrams, and see that together with the system level execution. That makes it really easy to see that the application works in a good way, it's efficient, etc., and it runs the way you intended, or if there is something weird going on. Another aspect is to find kind of violations of best practices. Developing multi-threaded software is pretty hard, and there are a lot of best practices in the industry that are important to follow. Otherwise, your application might become inefficient or unstable. And in a development team with people with different backgrounds, it's important that all are aware of these best practices and actually follow them. And having a way to detect deviations can be really useful, so you can learn from the mistakes and improve. Examples of this could be like bad scheduling patterns due to bad priorities, for instance, unsuitable priorities. Could be that someone is using a busy waiting function instead of suspending tasks, or that you could have kind of chaotic behavior in the system due to timing variations that change the order of events. And that's really bad for testability. You want the system to be as deterministic as possible. And of course, a tracing solution can of course be used to measure software timing, resource usage, performance, and other quantitative things like that. But the really cool thing is that with a more advanced solution like this, you can also see the reason behind the numbers. Like I showed you before, here we have this high response time. That's interesting to know, but you can also see why by focusing on this in the trace view. So this way you can find bottlenecks and optimize the application for much better performance. And this, of course, provides a better user experience, or you can actually choose to use a more cost-effective processor that is more power efficient or more cost-effective in terms of bill of materials, so your profits actually improve. And in general, software optimizations like this can often be quite small changes. If you have the sufficient insight, you can gain major improvements by making the right change, and it could be just a single line of code, like changing a scheduling priority or something like that. But the important thing is that you need to know how the system is really behaving in runtime and why. And if you can see that, then it's easy to improve. Here is an example of what we can see in the Tracealizer. Information like this about scheduling and API calls is captured automatically, basically, by the kernel instrumentation. And the Zephyr kernel has tracing hooks that our tracing library is hooking into and capturing information about these events. So you don't need to add any explicit instrumentation yourself to capture this information. That's what I mean by automatic here. You still need to enable the tracing though. We can see thread scheduling, of course, and also the labels here show information about API calls, what we call kernel services. And we can also see the status of the operations, like if there are blocking, shown in red here, and when blocking resumes, and if there are timeouts, those are shown with orange labels. This information can also be shown in other ways, like this in the CPU load graph, where we see a summary of the CPU utilization over time. So the peaks here are basically busy periods where we have a lot of activity. The way this works is that the time is divided into a number of slots. I believe it's 50 by default, and then within each slot that is not visible here, each interval here, we calculate the amount of time spent in each task or thread. This means that if you zoom in, then the size of these intervals change, so the absolute levels we can then change a bit. But this shows a kind of approximate view. CPU load is always relative to a certain resolution. Communication flow. This is kind of my favorite. I love this view. It gives a summary of how the different threads are interacting in runtime through different objects like semaphores and queues. This is a summary of the API call tracing, basically. Each API call is essentially a connection between a thread and another object, like a mutex or a semaphore. And if you treat that as a graph, then you get this picture. And the links, the nodes here in this graph are actually interactive. So you can click on a node like this, and then you get the object history view that shows you a focused perspective on for each event, for each object, like a certain queue or a mutex, whenever it's used during the execution. And if you click on those, you can see the context in the main trace view and see the big picture, so to say. You can also get timing statistics like this, and the extreme values, the minimum and maximum values, that is the ones we have noticed, not the theoretical maximums. They are links, so you can click them and see, focus the trace view on those points, like this. So here we can see that the execution time is at most 916 microseconds for this thread, but we have a response time of 103 milliseconds, 1,000 times more. So something is obviously blocking this thread, and probably a mutex or something. And we have a lot of different overviews. Here we see, for instance, a plot of response times, We can also see things like memory allocations and stack usage and things like that. Another way you can do tracing in Tracealizer that is very powerful in parallel with the kernel tracing is what we call user events. And this is explicit logging that you add in your code, very similar to a printf call, but the first parameter is what we call a user event channel name. That's only a grouping of these events, basically a label that organizes the data. So here we are logging in the a Bluetooth system. We are logging the signal strength of the nearby BLE devices, and we're using the BLE device ID as the channel name, and we're logging the signal strength as a signed integer, and it appears like this in the trace. And when you're logging user event data like this, then you can also see a plot of this over time. So here we can see how the signal strengths of the nearby devices are changing over time. And if you're interested in a particular point here, you can click on this and see the corresponding location in the trace where this is sampled. Another way to use user events is to capture kind of events on state changes and other synthetic events, so to say, that you're adding yourself for debugging. In this case, we're capturing state changes, in this case from this BLE stack. We can see we have events like ST scanning, ST connected, ST disconnecting, etc. So we have 3 different events, 3 different states, and in this these 3 swim lanes here, they show these states over time and how they transition between them. These individual entities are what we call intervals, the time between any 2 events that have been specified. In this case, it corresponds to a state, but an interval can be used to measure essentially anything. You can add your own user events anywhere in the code and define an interval in between them to measure the time. And we can get a plot like this to see where we see the different occurrences of this interval. We see that we have a baseline of about 50 milliseconds. That is the duration of this connected interval, connected state. But we have a few cases where we have 100 milliseconds or even 250 milliseconds. And if you click on this, then the trace view focuses there and you can see what happened. When logging states like this, you can also visualize the state diagrams, visualize the states as a state diagram like this, or a state machine graph as it's called in the tool. And this is a way to overview the state transitions, and you can compare it with your design and check that it behaves as intended. You can even generate this for a small fraction of the trace, I believe, and just make a selection and right click in the trace to get this view. So how do you enable Tracealizer support then? Well, first we need to enable the general tracing support. So we have different options for different types of events, and this can be used to filter the trace. That can be valuable sometimes when, depending on what channel you're using to transfer the data, you could sometimes the system might generate more events than you can transfer, and in those cases you will actually lose some events in the process. And if you see that, Tracealizer will give warnings about that, but in that case you need to reduce the amount of data somehow, and filtering on this level is then quite handy. Then we select Percepue Tracealizer support under Subsystems and OS Services Tracing Support. And if you want to, you can make some changes to the trace recorder configuration. At the moment, we only provide streaming support. In general, Tracealizer also supports something we call Snapshot Mode, where the data is stored in a ring buffer in target RAM. This is quite useful when if you stop on a breakpoint, then you have the latest trace up to this point in this buffer, although you can only get a quite short trace this way. Recorder start mode is you can select between start immediately or start await host. That means that the target, the trace recorder will block the target until you push the start button in Tracealizer. That can be handy for capturing the trace from the very beginning of the startup. You can do that with the regular start mode as well, but then you have to make sure that Tracealizer is ready to receive right away. Initialize means that the tracing won't be started right away, but only when you push the start command in Tracealizer, but there won't be any blocking or anything like that. The system will run as normal. You can monitor stack usage with Tracealizer as well. There is a periodic task that checks the amount of stack space remaining for each thread. In the bottom we have streaming port or stream port. Currently we have selected RTT streaming, which means Zephyr J-Link, but we also provide other ways to stream the data, other stream ports under the stream ports folder. To learn more, you can visit percepio.com and click on the Tracealizer link to find a lot of information there. You can sign up for an evaluation and get started right away. If you have any particular questions, you can always contact us at support@percepio.com. To use Tracealizer on Zephyr, you need Zephyr 2.6 as mentioned, and you need the very latest Tracealizer 4.5, and that's so new that it's not out yet. We provide the very initial beta support now in Tracealizer 4.5, and this will be released on June 15th is the plan, so about 1 week from now. You also need a physical channel to stream the data from the target system to the host, and this could be, for instance, a Zephyr J-Link, but other ways are also possible.